Hi there. Thanks for coming. So Casey and I are going to be speaking about protocol learning and how to use it to synthesize attacks. This is part of the work that we did in the Ensure program, and it's all been advised by Professor Pavlovich and Dr. Ziegler. So I'm going to start off by laying out the kinds of problems that we want to solve. Then I'm going to outline the approach based on learning. We're going to show a few prototypes of our implementations. Then I'm going to talk about one of the subtleties that arises with high-level protocols that manifest as vulnerabilities. And then we're going to zoom out to see where this kind of approach can be used in practice. So the problem of protocol development is that we're given a set of requirements governing interactions, and we want to develop a protocol whose interactions satisfy them. So the kinds of protocols that we care about largely come from, historically, from cyberspace. So we're talking about protocols for communication and for networking subject to security requirements. At a higher level, these protocols are used in societies and teams of humans and AIs and cyborgs and their computers and devices. And often it's necessary to think about this higher level if that's where the vulnerability is. But ultimately, we care about any kind of protocols that are vulnerable in practice and, for example, exploited by hackers and red teamers and penetration testers and people like that. So the observation about hackers is that even though they're not able to break cryptography, they often succeed at attacking protocols, either by subverting them from below or sublimating them from above. So the insight here is that a protocol interacts in higher level protocols, the ones that are using it, and in doing so, there's a real interaction across protocols. And the security claims of one protocol don't always exist, don't always extend to all of the ways that it's being used. And then from the standpoint of development, the way that we actually develop protocols and attacks in protocol analysis is through processes that are highly manual. And so what we want is an automated method that searches, given a set of requirements, for a protocol that satisfies them. It's worth noting that that the world of language modeling has already seen sort of what I'm thinking about that I'm calling protocol post-training. And the simple example is that after you pre-train a chatbot, it's able to predict the next token in such a way that the sentences it generates are syntactically correct. But it doesn't converse in the way that you would want. Right? Just training it for next token prediction doesn't mean it's automatically good at answering questions, right? It might ask more relevant questions. And so after that, we post-train the chatbot to perform the question answer protocol. And so through this post-training process, one of the things that it needs to do is learn this question answering protocol in which it plays a role that, after reading questions in the prompt, supplies answers in the responses. So question answering is one of the protocols that a chatbot must learn. Another one is following instructions of other kind, or refusing to address certain topics, or other kinds of tasks that we could, for example, specify in human annotated data sets of feedback. So chatbots, we've developed processes to post-train them to conform to protocols. But a lot of those protocols are really limited, right? They consist of two steps. Really, the only actor that we're post-training is the one chatbot. And in practice, what we want to do, and what hackers do, is to learn bigger protocols. So we want to extend the methods of post-training for protocols that are on larger networks with more roles, where the interactions that we're rewarding unfold over multiple steps instead of just two, and where what the roles are doing depend on their knowledge of what the other roles are doing. right? So there's a dependence among roles in a way that could be recursive. And in the real world, the protocols that we care about have some or all of these features, right? But we can hang our hat on the methods of post-training that we've already made for chatbots and individual models. And so what we want to do now is extend the methods that we've developed for post-training a model, extend them to develop methods to post-train entire protocols. And so what we're going to do in this talk is highlight some of the principles and the methods through prototypes that we're going to show. This whole idea of protocol learning inherits the risks from the relevant fields of study, right? It inherits risks from machine learning, from optimization, and from the theory of computation about what kinds of things are computable and optimizable in theory and in practice. So there's some problems that are just going to remain impossible. But we use these techniques because there's overwhelming success and proven guarantees about what kinds of things are possible in principle. And practice tells us how close we can get to realizing those like idealized upper bounds of capabilities. Right? So we benefit from the fact that humans are able to program things and that individual models are able to learn things. And now we want to do all of these kinds of things, but automatically and for protocols. So to sort of build up to what kind of structure is enabling all of this, it's worth clarifying what even an individual model does. Right? So we're working in a universe that has types. So here L is, for example, the kind of context that a model can have. And so a term in L is a context. So we have a bunch of different classes of contexts. And what a model does is turn context of one type to context of another type. Right? And the fact that we're doing this on computers means that all of these things are computable functions, although defined only on parts of domains. Okay, and then once we have a universe of types and computations, they're relatively well behaved. Right? They form a monodal category, which just means that if I have two functions where the endpoint of one matches the target of one matches the source of the other one, then we have a composite computation. And one of the things we have, for example, is if we have two contexts, then there's a product context for which a term consists of one term of each. So intuitively, if you're playing chess, there's like part of your brain that's playing this game of chess, part of your brain that's playing this game of chess, but in total, you're playing both, right? So you have context from both games. Okay, so now where does this come up in protocols? So first of all, what is a protocol? At the lowest level, it's a network about who exists in this universe we're considering and who's communicating with who. Above that is the process that describes what is actually being said on this network. So what computations a node is doing and what he's communicating to the other nodes. So this generates a whole bunch of possible traces of communication. And the logic layer specifies requirements for which kinds of traces are allowed to exist in this protocol and which are not allowed to exist. Okay. And then, so what is a network? At the lowest level, a network has a graph consisting of vertices and edges between them. And each vertex comes with its own type of context. So its memory could be either this or this or this, but it all belongs to a type of context. And each edge is a transformation for turning terms in this context to terms in the target context. So each channel above an edge has the source, which is the context type of its inputs, and the target, which is the context type of its outputs. So that's the graph. At the logic layer, as I said, there's hard requirements that the traces need to satisfy, and sort of soft preferences about basically rewards that we want to optimize. Okay. So now let's dive into sort of the dynamics of what a process is. One thing to note is that a chatbot can have memory. So in addition to whatever context it's building up from the conversation, it can also separately store memory. So each node has a type of state. And then what happens is when a channel fires, it sort of sends an outgoing message. I'm denoting this channel FU1V. And the message flows through to the node. And so the node can receive messages from this incoming channel or from any of the other incoming channels, or perhaps all of them simultaneously, or some subset of those. So a node is really receiving a tuple of inbound messages. Okay, and then it's outputting a new updated state and the sort of inputs that it's preparing for its outgoing channels. So it's preparing a tuple of outgoing inputs to those channels. So those tuples I'm denoting as living in SV, and then TV is recognizing we're passing those as inputs to the channels, and then calling the channels, which produces outputs for each outgoing channel. So that's TV. So you can think of a node in two different ways. In one of them, which I'm denoting with Fs, we statefully turn tuples of incoming messages to tuple of inputs for outgoing channels. And in the other way, instead of the inputs to those channels, we're returning the outputs to those channels. And so each node is running these computations. And for us, we're going to implement these with machine learning models. And so the first question you might ask as like a sanity check for intuition is, why is there any hope that protocols can be learned? And the sort of the most basic answer comes from one of the most well-known theorems in the theory of neural networks, which is that for any continuous function satisfying certain tight conditions that are basically always met in practice, there's a neural network whose evaluation approximates it. And these side conditions basically just say that you are trimming the inputs. So I'm not going to accept inputs from minus infinity to infinity. I'm going to assume inputs are coming in between minus 1 and 1 or something like that for each, so on bounded sets. Okay. And so there's two different kinds of learning that we want to do. One of them, which is sort of the model that we inherit from Ada Lovelace, is that, well, there are functions out there, and we want an implementation of one. And so our job as programmers is to learn a model or a program that implements that function. So if you knew what the optimal strategy for chess was, then a chessbot is just a program or a model that implements that function. And there probably is such a function, but we don't know what it is, right? So that's the kind of computation that Alan Turing talked about, which is what we call intelligence, that we are not getting it to learn sort of a prescribed behavior or function that we already know, right? We're using intelligence because we don't know. What we do know is what we want to accomplish, and what we want to learn is any model that satisfies a requirement. And so these are the two different kinds of sort of programming tasks. On the left, the satisfying intended behavior is often what we do in pre-training, right? For a language model, we know what it looks like to predict the next token and for sentences to be syntactically correct, and so we can just learn that, right? That amounts to learning a crystallization of language. But when we try to get these models to do things that we don't know how to do, like solve new problems that are very unlike those that it has seen, then we're not learning a sort of behavior that we already know. Instead, what we're doing is rewarding it when it's doing that to try to elicit that more. And that's what we're doing in post-training and in this talk. So I'm going to, so we're post-training protocols. So what are our models? Fundamentally, in this talk, they're transformer neural networks with positional encodings, unbounded context windows, and unbounded memories, which basically means that in addition to the actual forward path, we're also storing, for example, key value caches that can grow and we can update to be as big as needed. And but instead of transformers, we could have chosen RNNs or LSTMs or any other universal model, universal class of models. So what do I mean by universal? What I mean is that when we have a transformer that's computing how to transform context of this type to context of that type, well, then there's a way to evaluate transformers in such a way that for any function that does this context to context transformation, there's a model that implements that function, which means that for any context, feeding it as input to the evaluated model is just feeding it as input to the function that it's supposed to be implementing. So transformers are universal in the sense, which basically just means if you think about them as sequence-to-sequence functions like we do in natural language, any computation that we could do with a Turing machine, we could have done with a transformer. And that's sort of the way that the proof of universality works. So what does that mean? It means that for a function, all of these things are the same. Being computable means being programmable, in the sense that there's a program in a Turing machine or in a C program that implements that behavior. But for transformers, it means that it's realizable by that transformer. And because the way that we design models is by learning, computability means learnability. And to the high-level structures that are our class of models, the models are programs in a monoidal computer, in the sense that the programs are universal. And because of learning, we can learn the models that we want. And so the upshot is that the methods of high-level reasoning about computability can be extended to concepts and equivalent facts about learnability of models, and by extension, learnability of protocols. And a lot of the high-level reasoning results are formalized, for example, in this book that I'm citing. By Pavlovich from 2023 called Programs as Diagrams. And sort of the reason I'm talking about categories and computability in the first place is because they give us very concrete results about the kinds of models that we want to learn in practice. And we're going to see that very soon. So I'll start with the simplest fact. The simplest fact is we know what it means to implement a function. We want to implement a protocol. What does that mean? A protocol implementation assigns a model to each of the computations that it's supposed to be doing for transforming context. And so the conjecture is that whenever we have any protocol where these context-to-context transformations are computable, and they can be non-deterministic and partial and whatever, then there is an implementation. An implementation means that there's a model for each one, such that when you feed it any state and any context, input context, you get the same result whether you feed those inputs into the evaluated model or its computation. And this is exactly just the result about universality of transformers being applied to each computation. And so just as a picture, what we can have is if we have 3 nodes, each of which can talk to each possibly to some requirements, we know what transformations are supposed to be happening at each node, then each of them can be implemented by a model. So we can think about the computations, or we can just slot in one program for each node. But what actually do we want to learn, right? If G2 is like adversarial and it's trying to game G1 or trying to collaborate and cooperate with G1, then G2 might depend on the program that's running on G1. So what if that's the case? Then in general, we need to scale up the protocol implementation result to apply if some of these GI depend on models of other roles. Right? So these models can depend on, these roles can depend on models, and these dependencies can be filled by the models of roles. So this is very different than the usual sorts of ways that we think about AI agents and RL agents, right? An agent is something that we sort of train once and then just let it run, right? It operates selfishly, autonomously, and sort of independently. It like doesn't really know anything about what's going on. But in a play, you have an actor who knows what everybody else, the roles that everybody else is playing. So an actor is performing roles and protocols that depend explicitly on the roles of actors. And with those actors, it is possibly cooperating and or defecting, attacking, learning from, and ultimately using all of this to adapt the own role that it is performing. So often, if it's sort of in a system where the implementations of the other roles are known, then it can just use it, right? If it knows, oh, this chatbot is just running this open source model, we can post train on that to sort of game it. But if we don't know, if we don't have perfect information about the other model, and we certainly don't have its state usually, then the actor is playing a game with incomplete and imperfect information. So when we think about AI actors out in the world, then AI security is about actors and their epistemic games of incomplete and imperfect information within an isolated protocol, within like whatever situation it's in, but also across multiple protocols that could be interacting with each other. And so this is sort of the mindset that AI security is in. Okay. So what we're trying to show is that when we have protocols where the roles depend on other roles, that we still get an implementation that is sensible in the sense that I described on the next slide. For each protocol, suppose one of them has n nodes in the network, and suppose one of the nodes depends on n models and its own dynamic state, where it's going to feed as input to those n models the ones running on the other roles. Then what do we get? Then we get, because of this high-level reasoning that we could do from universality, we get a cleaning fixed point, which means that this cleaning fixed point is just a model. And so if you focus on the right-hand side of the equation, when you run the model, feeding it inputs where you're feeding its own self into the nth argument, you get the same thing as just running that role G with those same inputs. So in this sense, G sort of encodes its own behavior of what it would be like if it was running in the presence of those other n-1 models. Right? So this is called it's called the fundamental theorem of protocol learning because it's an application of sort of the same theorem called the fundamental theorem of computation, originally proven by Kleene in 1938 in the context of partial recursive functions, but we get it for free from transformers because of universality. And the proof, which you can find in chapter 3 of Pavlovich's book on programs as diagrams, there's a formal proof, which is just a high-level picture on one page that proves this result for an arbitrary model of computation that's universal, like transformers. And so thinking about these pictures is sort of a natural thing to do, and in this case is going to help us explain why you can implement these models for sort of recursively defined roles. And instead of diving into the details of partial recursive functions, we're just leveraging the high-level structure of universality and avoiding those low-level details, right? So I'm not telling you, oh, when these are the transformers for these models, here's exactly what you need to do to each of the weights to get the right one, right? We're not doing this low-level programming the way that Kleene did, and we're not doing it just for transformers. The same theorem automatically applies for LSTMs or GRUs or RNNs. And the reason why that's useful is that often, like a programmer is not dogmatic about what model he's going to use to solve some problem, right? It would be a shame if we had this universality for transformers, but then realize that, oh, this transformer is just overkill for my problem. I want to use a GRU. Well, the same result applies. And that's one of the benefits of thinking at this sort of higher level picture. Okay. So what that gets us is, because we have a universal evaluator for transformers, then there exists a partial evaluator, which has the property that when you think about one of these roles, which, as we said, has a Kleene fixed point, when you partially evaluate its cleaning fixed point on n minus 1 models, you get the transformed model. And it has a property that when you run it, it's the same as just running the model on those inputs with those models. Right, so this is like the usual notion of partial evaluation. What we're saying is you can partially evaluate your model on other models so that when you call it, you're like baked in calling those models. But you're doing this with a single program, right? So the single gamma automatically knows, the single gamma, when you partially evaluate it on those models, now when you run it, it knows to run it with that behavior. And because it's a cleaning fixed point, it's just the same as running G with those inputs. And so the magic of partial evaluation is that we're baking in all of this information about the other n minus 1 models into one. Okay, and so what we're going to do now is we have a protocol with a bunch of participants and the special one that knows about all n of them. And we're going to consider a like alternative version of it in which we, instead of just calling it with the nth model, we're going to partially evaluate the nth model on the other models. Then this GW hat has a cleaning fixed point, right? That implements little GW hat. And when you partially evaluate its cleaning fixed point on the honest implementations of the other participants, then you have the property that, well, A, the other models just honestly implement the computations that they're supposed to, right? They're like an honest implementation of the roles. And this partial evaluation is a single model that bakes in all of the other ones so that it's implementing the role that it's supposed to with the inputs that it's supposed to. So the single model GW has sort of recursively has the knowledge about how it should be running in light of the other models that it's running with. Okay, so just to zoom out a little bit, what we said is for any protocol, there exists an implementation of the roles, but a protocol also has requirements. So we can think about the requirements as, well, it's taking those models and it's telling you yes or no. Does it satisfy this requirement? Yes or no. So we have M requirements, N roles, but the same theorem says that any implementation says that there is an implementation that satisfies the system of equations, right? Which we can lay out this way, right? Each of the requirements depends on the models running on the roles, and there's a single program for each of them that just honestly implements this requirement, which means when you give it those inputs, it says yes or no. And each of the roles, even if they all recursively depend on each other, are going to have a single model that faithfully implements it for this choice of what is running on the other ones. Right, so this is like a higher level result of the one that we just showed, but it's exactly the same. The idea is that each one of them is basically partially evaluates on all of the other ones, and so this works for all of them simultaneously. Right, so this is useful if say some of them are just doing their role, but 2 or 3 of them can actually recursively depend on each other. So this is a general setting where we might be trying to learn more than one role at a time. Because, for example, maybe one actor is controlling 2 roles. And so what we have often is we have a bunch of models that are given, and in the simple case, in like the Ada Lovelace case, we know what the last role is supposed to do. It's supposed to say minimize the sum of the outputs of the other models. Okay, then we can just learn a model that approximates it. What we're doing is, even if we don't know what role it's supposed to do, we just know it depends on the other models, and we know what the requirements are. then there is a model for it that implements the system. And if the requirements are satisfiable, then there is a model that satisfies the requirements and optimizes the preferences. And so we want to learn one that does that. So that's the sort of single model case. In general, we might be trying to do that for multiple models. So the joint task is to learn all of the ones that you don't know. And the result of Smolean's fixed point theorem is that solutions really exist. So this fixed point theorem is the main thing doing all of the legwork in this presentation. It's saying that there are honest implementations of the roles that honestly implement the roles, and implementations of the requirements that honestly report whether they're satisfied. And if the requirements are satisfiable by some tuple of models, then there really is an implementation to learn that will satisfy the requirements. Okay, so I'll give sort of one example of a protocol that you might want to learn. So this concerns the Monty Hall problem, which I can explain in detail Q&A, but I'm going to assume for now that you know it. In the Monty Hall problem, the host has some way of operating. It's obeying some protocol, and the contestant chooses his own protocol about how he wants to interact with the host to optimize some quantity. And so in the left, I'm showing what I'm doing is I'm tweaking the protocol of the contestant. Originally, the reward for the protocol that he knew was only 1/3, but I am able to train it to get that quantity to 2/3. And for the Monty Hall problem, you can show that that's optimal. And so the plot on the right is evaluating it. Originally, when the model didn't know anything, its original protocol was successful 1/3 of the time. But after training, it's right 2/3 of the time. Right? So we can think about the Monty Hall problem as a problem of learning the role of the contestant that is optimal for this host-contestant protocol. And we can do it. And so what does the actor need to learn to do this? Right? It needs to sort of implicitly learn to do Bayesian reasoning. And so that's what's happening over the course of training. Okay, I'll give another example of another kind of protocol that you might want to learn. So you can think about the three-way handshake for TCP, which consists of SYN, SYNAC, ACK. Or I sometimes think of it as this protocol. You say, "How are you doing?" And then they respond, "How are you doing?" "I'm good." And then you say, "Good." And then now you've done the three-step handshake and you're ready to proceed with polite conversation. So that's the three-step TCP protocol. You can also sort of add more information to it, and a refinement of it is the original Needham-Schroeder public key protocol, where in addition to just sending SYN, SYNAC, ACK, you are sort of encrypting things in such a way that at the end of this handshake, you've authenticated each other. And so you can think at any point, any of these actors can send sort of encrypted messages with whatever information they happen to have, and the question is, what is the way of sending messages for which you satisfy the requirement of mutual authentication? And so this is the way. And then the question you would ask is there any way to use this protocol to break the claim of mutual authentication? And there was a period, I think for about 4 or 5 years, when we knew about this protocol, and we sort of knew about the vulnerabilities of receivers and adversaries that are able to manipulate or relay messages. But in those 4 or 5 years, we still didn't know what the actual attack was until Lowe discovered an attack on this protocol, which I can go over in Q&A. And the question is, if we sort of knew that an intermediary actor could relay, like we knew that was one of the message types that he could sort of intercept and then send that message back or send it to whoever else. What is the actual way of using relay to break the mutual authentication claim? Okay, this is one way, but I'll show that we are actually able to use the same method that we use for Monty Hall to discover this impersonation attack. So in the beginning, we, in this test plot on the right, you can see our way of choosing actions of what to send was so bad that we broke the claim 0% of the times. And then by the end, we had a stochastic policy that was right 99 out of 100 times. And if instead of sampling, we just chose the best one, then it was right 100% of the time. Which means that whenever the model is set up right, whenever we situate the actor so that it is communicating with two honest actors, we have a deterministic policy for violating the claim in such a way that one of the actors thinks that that they're communicating with ours, but the other one thinks that it's communicating with the first one instead of the impersonator. So we're able to learn this impersonation attack. In the beginning, we sometimes stumble into it, and then once we've stumbled into it, we can sort of make our knowledge of it more concrete. So what is this showing? It's sort of, if you think about a single instance of the protocol, when all actors are honest, then it's secure. But we can use this in this higher level setting where an adversary is running two instances of the protocol. And so in this higher level setting, it's like there's two instances of the protocol that are interacting with each other in a way that was not anticipated, and in such a way that this higher level protocol broke the claims of the lower level one. And so this kind of phenomenon was articulated very clearly in a paper called Protocol Interactions and the Chosen Protocol Attack in 1997, where they said you can have this effect where a target protocol can be secure in isolation, yet attacked by a chosen protocol that interacts with it. And the prime example that the paper focuses on is if you, for example, use the same encryption program with the same keys in different applications, then there might be an interaction between those two that violates requirements. So in this example of the chosen protocol attack, you have to sort of construct the second protocol with a correct role that depends on the model running in the other protocol. And the attacker would have a hard time just learning the model. But if he can design the right role in this chosen protocol, and the attacker supplies their model into it, then this role can just run it, right? If HGK is just run GK, then now he has a model that he can use to impersonate the victim in the target protocol. So if what you want to do is an impersonation attack, then the role in the chosen protocol is very easy to learn. But usually we have the other dynamic where you know the roles running on the protocol, but you don't know what to do to exploit it. And so in that setting, what you would do is you would recognize that there might be a vulnerability to cross-protocol interaction, and maybe hire smart people to figure out how exactly to use knowledge of the models to exploit it via cross-protocol interaction. But what we're saying is, as we've shown with Monty Hall and with the Low attack, we can use an automated method to just initialize a protocol and then post-train it until it is good at attacking. Okay, so how do you do that? You start with a target protocol and then extend the network, and then you say, well, what I want to do is contradict the preferences. And then to learn the model, this is the optimize the preferences, you initialize them, and then you test how good it is, then update and repeat. And so in fact, the reward that I used to discover that attack on the NSPK protocol, my reward literally was assign a large negative reward if the adversary uh, accidentally performs honest authentication in each of them, and assign a small positive reward if it does anything else. Well, then the model learns to not do the honest thing, and because we're giving it a reward for exploration, and there is an attack, it happens to learn it. And then I'm also assigning a large positive reward for actually breaking, for actually deceiving one of them into, um, actually deceiving one of them. Then once it, because that reward is so large and positive, once it has accidentally stumbled into it by exploration, it's able to do it more reliably. And so that's sort of the way that we can synthesize attacks. And but it's not a magic bullet, right? What we want is protocol secure against higher level protocol learning. But in the real world, like low level crypto protocols can be secure if designed properly and implemented properly and configured properly. Then there might just not be an attack like that. If attacks exist, they're typically in higher level protocols, like the one that chooses to use this parameter instead of the default. Right? If you do use the default, then that higher level protocol is could be like very clearly insecure. So this is not a magic bullet against real crypto protocols that are properly designed, implemented, configured. But at this higher level, these higher level security protocols often are vulnerable, sometimes by necessity. So this happens in the real world when you think about secondary screening protocols. There often we actually don't have logical requirements that we must satisfy. Instead, in practice, we have preferences. Like this is how much money I'm willing to spend to guarantee this sort of tested level of security for border security, right? Because they don't have infinite budgets, we actually set preferences. And same thing for airports and elsewhere. In cybersecurity, we might have hard requirements for low-level crypto protocols, but that is not the case for high-level protocols of intrusion detection or incident response, or for other kinds of protocols with these kinds of potential vulnerabilities. One of them is that the roles, if the roles are just not specified or ill-specified or not enforced, then that is a kind of protocol that would be vulnerable to protocol learning. Another one is if the requirements are inconsistent, for example, because you've extended it and the claims no longer hold, or the requirement that you cared about just wasn't specified and not actually secured. Another one, like I mentioned, is you could have conflicting preferences, which often arise when you have trade-offs. And for a high-level protocol, right, the saying is that there are no solutions, only trade-offs. And this happens a lot when you think about protocols where we like have explicit roles played by humans or AIs, right? Why would we have that instead of a computer program? Because we just don't actually know what to do, right? For incident response, there's often this high-level strategic element played by humans because the correct behavior just is not written down anywhere. Maybe you could train AI to do its job, but still, if you're using AI instead of like a concrete, like rule-based system, it's probably because you actually are not sure about what the AI should be doing. You only know that you've taught it in some way. And so if there's an AI in the loop, there's like a strong chance that there's a sort of AI method for counteracting it. So what have we covered? I've shown that attack synthesis is protocol learning, and that that's a problem that we can actually solve in practice. I've shown that with 2 of my demos, and Casey showed that with hers. The benefits of protocol learning is that we've also shown, because of the universality of transformers, that there's a sense in which learnability is computability. And so that gives us high-level reasoning about things that we use in this talk, like fixed point, and roles, and actors, and recursion, and dependence. And those are exactly the things that you need to explain the phenomenon discussed in the chosen protocol attack. And again, these methods for protocol learning actually exist, right? We do it with algorithms for constrained joint optimization that in practice scale with availability of data and compute. Okay, so going forward, there's sort of two kinds of directions. On the one hand, we can continue with this slogan that learnability equals computability and mine it to get like basically free consequences from computability theory that could be really meaningful for learning and protocol learning. And so one direction is figuring out what other kinds of things we can do. And then on the practical side, once we can do protocol learning, what we actually want to do it on is we want to use it to learn attacks on target protocols and to sort of think about which of our protocols are vulnerable to these kinds of attacks and learn the like thresholds and models and entire protocols for security that maximally resist these attacks. And those are exactly the kinds of problems that we want to solve next. Okay, I'm now open to all forms of questions and feedback and advice and anything else. Any other comments? Thank you.